Welcome back. In this video, we'll discuss section 8.1, Understanding Functions of Two Variables. Up to this point in the course, we've only looked at a function of a single variable, something of the form y equals f of x. In real life, though, most outcomes depend on more than one variable. So let's now consider a function of two variables. I could write z equals f of xy. Notice now both x and y are playing the role of independent variables, and z is the dependent variable. So we need to plug two things into this function, x and y, to get an output z. The collection of all possible inputs, or ordered pairs x comma y, is called the domain of the function f. Now, what do you suppose the graph of a function of two variables looks like? Well, it's a surface. So let's start by drawing the coordinate axes, the x, y, and z axes. The xy plane is the horizontal plane. So kind of think of that as the surface of your desk or table. And then the z-axis is the vertical axis rising out of the top of the table. So I've drawn a surface here I'll call it a magic floating carpet. And notice the output z is the height of the surface at the point xy. So we've got this ordered pair xy, which maps to a point on the surface z. Next, I'd like to talk about what it means for a function of two variables to be increasing or decreasing. And to motivate this, we'll look at this example. I've got a surface drawn here that kind of looks like a dome. Notice it's a little bit longer than it is wide. Y is running from -4 to 4, where x is just running from -2 to 2. So let's do this. Let's fix x equal to 0 and let y vary. So if we do that, we're going to just be moving left and right along the y-axis here. And what we can do is draw what's called a cross-section, which you could just think of as a vertical slice. So if we slice this surface along the y-axis, we're just going to get kind of what remains of the surface in the yz plane, or the intersection of the surface with the yz plane. So it's just going to be this kind of arch right here, and I've recreated it here. The cross section would look like this. And what you see is as y goes from -4 to 0, the outputs z are increasing. So we would say that f, or f of 0y, is an increasing function of y for y between -4 and 0. And notice as y increases from 0 to 4, the outputs z are decreasing, so we'd say f, or f of 0y, is a decreasing function of y for y between 0 and 4. Now let's fix y equal to 0 and let x vary. So now we're going to be moving along the x-axis here, and a cross-section would be the intersection of the surface with the xz plane. So it's going to be this arch that you see here. And I've redrawn that below. Right here is the cross-section. And what you see is for x running from -2 to 0, the outputs z are getting bigger. So we'd say f of x0 is an increasing function of x for x between -2 and 0. And then as x increases from 0 to 2, the outputs z are getting smaller. So we'd say f of x0 is a decreasing function of x for x between 0 and 2. Let's look at example 2 from the text. A car rental company charges $40 a day and 15 cents a mile for its cars. So notice the cost of the car depends on two things, the number of days that it's rented and the number of miles that it's driven. Let's write a formula for the cost, C, of renting a car as a function of the number of days, D, and the number of miles driven, M. So we could write C equals F of D comma M is equal to 40D. Each day you rent the car, you have a cost of $40 plus 0.15 M for each mile driven. There's a cost of 15 cents. Exercise 1 involves the same example, and it says make a table of values for C using the values D equals 1 through 4 and M equals 100, 200, 300, and 400. So we're going to get this table with 16 entries, and to find this very first entry, when D is 1 and M is 100, I've got the work shown off to the side. F of 1 comma 100 is 40 times 1 plus 0.15 times 100, or $55. So we could find the other entries in a similar fashion. Notice in row 1, as you move this direction, we're holding M fixed at 100 and letting D increase. And if you look at the other entries in the first column, we're holding D fixed at 1 and letting M increase. So exercise 2 involves the same example. Part A, find F of 3 comma 200 and interpret it. Well, we'd use that formula from above. F of 3 comma 200 is 40 times 3 plus 0.15 times 200, giving us 150. And the way to interpret it is if we rent the car for 3 days and drive a total of 200 miles, it costs us $150. Now in part B, what we'll do is we'll hold D fixed at 3 days and let the number of miles driven vary. And what we could do is sketch the cross section. It'll look something like this. I don't know exactly what the surface C looks like, but this cross section will be a vertical slice where we hold D fixed at 3. And notice I've gone back to the formula for C. F of 3 comma M would look like this. It's 40 times 3 plus 0.15 times M, which reduces to this, 120 plus 0.15 M. So this is just a line with vertical intercept 120. That's what you see here. And slope equal to 0.15. So we see that C is an increasing function of M. Now let's hold M fixed at 100 and let D vary. So we would have F of D comma of 100 equals 40D plus 0.15 times 100, which is 40D plus 15. So this is a line as well, and we can draw the cross section. The vertical intercept is 15 and the slope is 40. So we see here that C is an increasing function of D. Finally, I'd like to say a little bit more about the domain and range of a function of two variables. Recall the domain is the collection of all possible inputs, or ordered pairs x comma y. We need to follow the usual practice of excluding inputs that lead to complex numbers or division by 0. The range is the set of output values for the dependent variable. So here's an example. Let z equal f of xy equal x squared plus y squared. Find the domain and range of this function. So in thinking about the collection of possible inputs, you have to ask, are there any values or ordered pairs x, y that we cannot enter into this formula? So we want to be on the lookout for division by 0 or something leading to a complex number. Well, that's not going to happen here. You can plug in anything you want for x and y, and you get a real number output. So the domain is all ordered pairs x comma y, or the entire xy plane. And for the set of output values, because we're squaring x and squaring y, you're never going to get a negative output. You may get 0 as the output if both x and y are 0, but you'll never get a negative output. So the range is the set of non-negative real numbers. And I have a display of the graph of this surface here. Now I've kind of restricted the domain to this box -2, 2 for x, and -2, 2 for y. Well, we could extend that indefinitely in either direction. And what would happen as you do that is this surface would get taller and taller. But notice the range is, as we saw, it's all non-negative real numbers, 0 and everything greater. So we'll stop there for now. See you next time.